Alright, we're going to take a quick tour of probes and how to use different types of probes, primarily simple passive probes with your oscilloscope and why you need to use them. So we've got to think about, if we're going to connect up our scope to our circuit, how do we do that? Well, you might just say, well, why don't I just use a simple set of probes like I use with my voltmeter, right? I can kind of put them together in this little adapter here and stick it on the front end of the scope. So let's do that. Let's look at what happens. So you can see the scope trace is kind of all full of noise. It's picking up all the 60 cycle hum from my lab bench here and all the lights and things like that from the ballast and the fluorescence and all kinds of nasty noise. And that's the problem. If you're trying to look at low-level signals and things like that, connecting up with leads like this is going to present a number of different types of problems. And let's look at why. So it helps to start off by looking at what the scope input looks like. So that's kind of what the oscilloscope input looks like. It's basically almost most of the scopes will have a 1 megohm input impedance, so basically right behind the front panel connector it looks like a 1 megohm resistor to ground. And that's typically got in parallel with it anywhere from 10 to 25 or 30 picofarads of capacitance, sometimes a little more, sometimes a little less. Okay, so it's a pretty high impedance, just like your voltmeter is, but it also has a lot more bandwidth than your voltmeter, so it's going to pick up all kinds of things. So if we just connect up the wires like we just did, this is what happened here. So we connected up these wires. They basically look like big antennas, okay? And so even if we connect it up to a circuit, if the circuit's not low impedance, you're still going to be injecting noise into your circuit, and you're also going to be injecting noise into your measurement, okay? So it works, you know, as long as your signals are really low frequency, okay, or you've got some really large signals you're dealing with. Otherwise, you're adding a lot of inductance into the measurement path. You're picking up all kinds of stuff with these wires and they're acting like antennas, and you might even couple some signals to other parts of your circuit. All things that are not really good. So typically why we don't use wires. So another way around that is, well, let's make these wires shielded, use a piece of coax. And if we do that, so now we can wind up with this situation here, and this actually solves some problems, okay? Because now that the signal wire is shielded by ground, we're not going to be picking up a lot of signals, so that's good. We're going to minimize coupling to other parts of the circuit, so that's good. Okay, but what's bad about this? Well, it adds a lot of capacitive loading. The way to think about this is that typical coax, the miniature coax you might use, like RG174 or something like that, may have 25 or 30 picofarads of capacitance per foot. And if you're talking 2 or 3 feet of cable, of coax to connect to your circuit, that coupled with the 10, 20 picofarads of capacitance at the input, you could easily add 100 picofarads of capacitance to your circuit by simply connecting the probe. Now, will your circuit care? Depends on your circuit, right? Sometimes it will. You have to remember that 100 picofarads at looks like 50 ohms at 30 megahertz. That's a far cry from the original 1 megohm input impedance that we were dealing with to begin with. So, but this is a basic 1X probe design, and they're out there, and you just got to be careful when you can use them and when you can't. Just take care, and understand the ramifications of touching this probe to your circuit and how it will affect it. Think about would I want to solder in 100 or 120 picofarads of capacitance to my circuit at the point I'm trying to measure. Okay, and expect the circuit to still work. A lot of circuits, will work just fine. Audio circuits, low frequency things, lower impedance circuits, and generally might be okay. But for a large majority of circuits, the amount of loading from a 1X probe is not going to be good. The capacitive loading could really affect the circuit operation. So how do we isolate the capacitive loading of this type of a probe, a 1X probe, from the circuit? Well, one way to do that is to stick a big resistor in series with that. So we stick a 9 megohm resistor in series with the coax. What that's going to do is now all the capacitance is sitting back here is really kind of isolated away from the circuit we're testing over here by this 9 megohm resistor. So your circuit really doesn't see it. So that's good. Okay. Now the resistor, we chose 9 megohms because it gives us a nice convenient 9 megohm to 1 megohm resistor divider here. So it's a 10x resistor divider. Hence that's the reason why we call this a 10x probe. It doesn't have 10x worth of gain. It has 10x worth of attenuation. So it'll attenuate the circuit, but or attenuate the signal by a factor of 10. But that's pretty easily compensated for. But it also reduces the capacitive loading, so that's good. Now the problem that you can run into, though, is that the 9 megohm resistor, okay, and the capacitance of the coax and the scope form an RC low-pass filter that looks like this. Okay, and what happens is as the frequency goes up of what we're looking at here, the capacitive reactance here starts going down, and all of a sudden this, the 10x divide ratio that we had because of this resistor starts getting dominated by the capacitive reactance of that capacitor, and we start rolling the signal off. So it's a low-pass filter. So now as the frequency increases, our 10x attenuation got worse and worse and worse. So it didn't really help us that much, but there's actually, it turns out, a pretty simple fix for this, and this is what's typically done with 10x probes. So if we look over here to the last page here, what we do is add a compensation capacitor in parallel with that 9 megohm resistor. And the idea there now is that for low frequencies, the 10x attenuation is dominated by the 9 megohm and 1 megohm resistor. Okay, so that kind of dominates our 10x attenuation. But now as the frequencies go up, okay, the capacitive reactance of the scope input and the probe cable is going to start dominating the input impedance of the scope, and then so what we do is we add a compensation capacitor here, which kind of will now track that. So now at higher frequencies, if we make the ratio of this capacitance to this one 10x, okay, now that capacitive voltage divider is going to dominate the attenuation at high frequencies. So now between low frequencies and high frequencies, we've got still 10x attenuation. Okay. Of course, the input impedance at high frequencies is going down because this looks like this series combination of capacitors. But at the end of the day, the probe is still flat in frequency response generally. Okay. So we basically can account for that, and this is basically the design of commercial 10x probes. Now they're called 10x probes because they attenuate by a factor of 10. So that's something that's important. You've got to think about that, is that when you connect this probe up to your scope, you've got to remember that the probe is actually attenuating the signal by a factor of 10. Some scopes and probes help you out with that and actually remind you that that's what it's doing, but most of them don't, especially the lower cost ones. So if we connect up we'll look at some typical 10x probes here. Let's go take a look at some of these. I'm going to clear out these other probes, DMM probes, out of the way here. And let's look at one. Here's a 10x probe. This is a Tektronix P6105. Okay, it's a 100 megahertz 10x probe, 2 meters long. We'll take a look at, this is the part that would connect up to the scope. This is the part that would connect up to your circuit. There's your ground lead right there. A lot of these have got removable spring clip tips, so you can be probing around with the tip here, or you can connect this up and you get a nice retractable clip, so you can clip this thing into your circuit. Okay, number of different variations on this set of combinations, but this is typical of what you'd find. Now, either on the probe handle itself, like this, or on the compensation box or probe body here, you'll find the compensation adjustment. If we look in this one here, we can actually see there's a little screw with a trimmer cap to set up the compensation for that probe. Here's another example of one here. This is also a Tektronix. This is a P2220. There's our compensation adjustment right there. Okay, and there's our ground lead and our probe to be able to connect up. And we'll look at a couple of other examples too. But one thing I wanted to point out that's different between these two, if you look carefully at the end of these, I don't know if you can see in the camera or not, but there's a little metal pin sticking out of this one. There's not sticking out of this one here, but there's a little metal pin sticking out of the end of the connector here. And what that is, it's something that Tektronix called the Tech Probe interface. And for scopes that were so equipped, when you connected this probe up to the scope had a little sensing ring. In fact, we can look at that over on this scope over here. There's a little sensing ring right around the BNC connector here. And that BNC connector, when that little pin connects to that, that would tell the scope that this is a 10x probe that's being attached, and would adjust the scale appropriately. Okay, most scopes, especially non-Tektronix scope, don't have that little sensing ring around the BNC connectors where you connect the scope up. So when it comes to making sure that, okay, is my scale correct for the 10x probe, you've got to worry about that yourself. So even if the scope channel says 50 millivolts per division like it does here, when I connect up a 10x probe, that is now 500 millivolts per division. Okay, it doesn't tell you that, but you've got to think about that. This probe actually has a switch on it, okay, to go from 1x mode, which is just basically a cable connection or coaxial connection right to the probe tip. That's going to have 100 picofarad capacitance or more, but it doesn't have the attenuation. And there's a 10x mode to do what we've been talking about. So now the trick is, how do we adjust that compensation capacitor, okay, to make sure that we match the input capacitance of the scope, because some of them are quite different. This scope here, that input capacitance might be hard to see, says 25 picofarads. This scope over here, that one says 1 megohm and 15 picofarads. So that's quite a difference. And they certainly, a scope that's matched to this scope here wouldn't necessarily match to this other scope over here on the right. So that's why that compensation capacitor is made adjustable. So how do we adjust that? Basically we use a little test signal, a calibrator signal, a compensation signal, and it's typically a square wave. The square waves are nice because you can have a fairly low frequency square wave that has very fast rising and falling edges, and what that gives you is a waveform that has a lot of low frequency components and high frequency components, because basically a square wave is fundamental, frequency of the square wave is energy, but then you've also got energy at all the odd harmonics at 3 times that frequency and 5 times and 7 times, etc. The more high order harmonics that you have, the faster the rising and falling edges. So it's a nice waveform that has both fast, or I should say high frequency energy and low frequency energy in it at the same time. And the way to adjust these probes is actually quite simple. Let's kind of look at the example over here on this scope. Okay. So in this scope here, I've got, this is a P6131 10X probe connected up to channel 1. And on this scope over here is our calibrator signal. Okay, and I've got the ground lead already connected. If we connect up the scope to it, or the probe to it, and we could take a look here at on the waveform. And this one is pretty well compensated. Now you may notice when you get a 10X probe, they'll always come with, when they're new, a little diddle stick, a little screwdriver. This one actually still says Tektronix on it, but it's just basically it's a little non-metallic screwdriver to adjust the compensation capacitor inside the probe. Like I said, sometimes those compensation adjustments will be on the probe body, and sometimes they'll be right on the the probe box that connects up to the scope. And this is the waveform that we're looking at here is typically what you'd ideally want to see, in that it looks like a perfect square wave. And here's what it looks like if you have it misadjusted. Let's see if I can engage the screwdriver in here. There we go. And you can see if I make that capacitor too big, okay, we're going to couple more high frequency energy in, and we're going to get this overshoot on the rising and falling edges of the square wave. And if we adjust it the other way, where that capacitor is too small, now we're low pass filtering that square wave, and we get this kind of rolled off response there. So the idea is to adjust this thing. If we kind of go back and forth, we can adjust that until we get a really nice looking square wave. And what we've done now is made sure that the low frequency response which is kind of set up by the resistor, is now matched by the high frequency response set up by the capacitive voltage divider of the 9 megohm resistor and the parallel capacitance, and then the cable and input scope capacitance. And now this probe will be good for looking at both high frequencies and low frequencies. But you'll notice again, this probe, if we look at the scope, you might see that the scale on the scope says 100 millivolts a division. If I remove this scope, this probe, you can see that drops to 10 millivolts a division. This probe has got that little metal pin, and this scope is automatically sensing that. There are other scopes that sometimes will actually have a little light that will tell you whether you've got 1x or a 10x attenuation, on some of the Tektronix scopes. But the non-Tektronix scopes typically don't have that sensing ring, or at least most of them don't. So if you put a 10x probe on there, you've got to multiply your volts per division setting by a factor of 10 when you're using the 10x probe in order to make a calibrated amplitude reading. So that's a quick tutorial on what 10x probes are and how to adjust them. Make sure that they're calibrated for anytime you change a scope, and you can use the same probe on a new scope, readjust that for that new scope, because no two scopes really match in terms of their input impedance, and properly adjusted probe on one scope won't necessarily be properly adjusted for another scope.